We have 1 minute to start with the next session. And I think Gavin had joined us a few minutes later. For those of you who are joining us just earlier, those of you who are joining us now, there is a link that was shared in the chat. I think I will just send it to everyone in a few, or maybe, yeah, everyone in a few. So this is the link to the data and the code for the live coding session. In case you're already using R and you would like to pre-install a few of the packages that are there, please feel free to go ahead and do so. And if you'd like to code us at the same time or just follow what he's going to be doing. So we're going to start this session. And this session is by Gavin Simpson. And Gavin is an assistant professor of applied statistics in the Department of Animal Science at Aarhus University in Denmark. He is a statistical ecologist with particular interest in spatiotemporal change in ecological communities and ecosystems and the methods used to detect them. He trained initially as a paleoecologist, and the statistical challenges posed by the paleoenvironmental data have shaped Gavin's subsequent research interests, which include trend estimation using generalized additive models and methods for summarizing and analyzing multivariate paleoecological data. So I will invite Gavin to just take us through the next session.
Okay, thank you, Tina. Thanks for the invitation as well to spend a little bit of time doing a little bit of our coding today. It's great to see so many people here, and it's especially great to see so many people's names who I don't know. Often I find myself talking to the same people within the paleoecological community, so it's great to see lots of new names here. People that I don't think I've met. Okay. So what we're going to do is I am literally going to write code. I've already written the code and you can see it, it's in GitHub, but I'm actually going to live code this. So you'll see how bad a typer I am. We'll see all the mistakes that I make and so on, right? Also, if you would like to see something, if something's not clear, then please feel free to either unmute yourselves and just ask. That's fine, just interrupt me as we're going along, or pop the question in the chat. I will do my best to periodically catch the chat, but if it's something that you really need to ask and I've not seen it in the chat, please just unmute yourself and ask, okay? This is going to be a bit of a free-form session, and with no formal slides, so we're just going to do some coding, all right? And I'm going to explain a little bit about what the methods are and what the code is, but we're not going to spend too much time on those kind of theoretical aspects. Okay, right. Let me share my screen then. Okay, so the link. Let's make this a little bit bigger. Hopefully, everybody can see this. So this is GitHub, and for those of you who are not familiar with GitHub, it's a kind of like serves two purposes. Website that allows for the archival of code, in a sense, it's an online repository, and it also does another thing. Which the main thing it does is which allows us to use, or we can use it without GitHub, but it's just a remote server where we can do version control. And so I think you'll start to see this a bit more in sort of open science-based activities is GitHub. But if you're not familiar with it and you don't know how to use Git, but you want to get the stuff out of my repo, then main thing is find the big green button and here, click on it. Okay, and then where you see the download zip, if you just click on that, it will then download a copy of the repo, the repository, in whatever state it's in on GitHub at the moment. And so, for example, if I was to make some changes and push some changes up there, you would have to come back in here and click the code button and download a new copy, all right? If you were used to using Git, then you'll know what to do with these things up here, all right? But if you've not used Git before and you want to get hold of the files, download the zip file, all right? And then once you've got this thing, let me open it in my folder. Okay. So it'll look like it's a zip file, all right? On Windows, because Windows tries to be really helpful, and I'm not running Windows, by the way, so things are going to look very different here. But if you're on Windows, don't just double-click this, because on Windows, it will take you into the zip file as though you've opened it, and you can work with it as though you've opened it, but you haven't, right? What you need to do is something along the lines of right-click on it, and then do extract here, extract to, unpack, unzip, something like that, and then it will extract the files for you. So on my computer, it's extract here, okay? And then you'll get a folder which looks now like, and has the contents that you can see in the web page here on GitHub, all right? Okay, let me just go back. Right, so, and then you can start your RStudio. In here, you could right-click on one of these files and do open with RStudio, and then RStudio would get you in the right folder to work with these files and so on, okay? Right, so let's switch to RStudio. If I can find the right thing. Okay, let's move off that. Yeah, well, never mind. Okay, this is RStudio, and it's an interface to R. So the thing that's running in this window up here is actually R. So this is the statistical software that we're going to use, and then everything else around it is RStudio. So RStudio provides this nice interface for us, and I will. Towards the end, actually, I'll do that now. Let's show you where to get RStudio. If you're a complete beginner to this, where do we get R from? So let's just go and have a look at RStudio first. So RStudio is open source software, at least the desktop version that we are working with is free and open source. And you go to rstudio.com, okay? And then we want to go and find the open source version of RStudio. Right? And if we click on this, what we want is the desktop version. So click on the big button. Okay, and now we can download it. And then when you click on this, it will offer you some other options because they also would like to make some money. You just click on download, and then you want to choose the version of the installation program for your computer. So if you're on Windows, let's make this a little bit bigger. Okay, so if you're on Windows, you want the .exe. Okay, if you're on macOS, you want this DMG file, and then if you are like me, a Linux user, then choose the version of for the version of Linux that sort of more closely matches your installation. Okay, but I suspect most of you are going to be using one of these two here. All right, now that just installs the RStudio. You need to also install R. So if we just scroll back up a little bit, it's telling us these options. So we need to install R, right? And if we click on this link, we'll get taken to the R website where R is located, where you can download it, and it will take you directly to the download page. And then you just need to follow the link for your particular operating system. So those of us using Linux, we can access it from here. There's for macOS or macOS. And there are different versions depending on whether you're running on one of these newfangled Mac machines with an M1 sort of chip in there, the ARM-based system, or whether you're using one of the Intel systems, the slightly older one. Okay, so just make sure you get the right one. Make sure you read the page. That's always a good idea. And then if you're on Windows, a little bit different, but you want to go into this base folder up here. And then there's this link, download R, and the version at the moment is R 4.2. You always want to try and keep up to date, all right, relatively up to date with your R, okay? I'm running version 4.1 point something at the moment. I'm not updated yet because this version only came out the other day, all right? So there's lots of help in each of these windows as well. So it's definitely worthwhile just paying a little bit of attention to the pages when you're going to try and download and install R. So you install R, the file that you download, like this file, or the equivalent for Windows. Let's go back to the Windows one in base. You click this. This is going to download an executable file. Okay, you would run that file. That would start up the standard installer, and then it would ask you a few questions, and you can just accept the defaults essentially. All right. So you do that, and then we have the installer for RStudio. We install that. And once you've got both bits of software installed, then you're ready to go. Okay. Now, you don't need to use RStudio to use R. You can just use R on its own, but it's really advantageous if you use what we call an I development environment, which is what RStudio is. And the reason for that, and I recommend anybody who's new to R and these sorts of things, is to use RStudio. Really user-friendly, helps you with a lot of things, and it just provides some access to features that you wouldn't necessarily have if you were just working in R on your own. Okay, and we'll explore some of those features now. Right, there are two things that we want to do. We want to make sure that we are in the right folder. All right. R has this concept of a working directory. So that's the directory that you're in, that R is working from. So I've got mine working from my folder on my computer, but I think we can go and I can go and have a look. I have that folder in my downloads folder, and then, and it could, of course, it doesn't sort the things. What do we call it? Pre something, didn't we? Okay, so here's that folder that I downloaded. Here's the zip file. I unpacked it. Here's that folder that I downloaded. Okay, if I want to start R working in here, I just navigate to it in this panel, and I go to More, and I can set my working directory to be this one. And that's the easiest way today to just have access to these files and work with it. All right. So there you go. So I'm going to be working in this repo that I downloaded. Okay. And there are these files. I'm not going to open them, but you can open them and have a look. They've just got some R code in them. I'm actually going to recreate that. And then in the data folder here, we've got a few data files that we'll be working with. All right. To go back up, just click the little two dots here. Okay. Right. The other thing that we need to do is that we should never be working in here. All right. We should, if we're doing things in here, this should only be stuff that we would expect to throw away. We're not going to have any record of this really. There is a history, but let's not worry about that. Anything we do in here, essentially, we should be prepared to lose it. What we should be doing is using a script. And the reason for using a script, which is basically just a text file that contains all of our R code that we want to have for a particular analysis, is going to be contained in that one script. And maybe you have, for a particular project, you might have 10, 20, 30 scripts that are all doing different things. But for simple projects, you might just only have a one R script per chapter of your thesis or something like that. All right. But the script is going to contain all of the R commands that you want to apply to a data set, to do the kinds of analysis, to create your plots that you want for a particular project. And the reason script is that we can save that file to disk, it can be shared with people, it can be stored in a website like GitHub, and then that's a permanent record, as long as you don't put your computer under a bus. That's a permanent record of all of the analysis steps that you did to create the results and the figures that you might have used in your thesis or in your in a paper. All right, and it's getting really important. I think we might have all heard about problems with the statistics that people are doing, the reproducibility crisis in science and so on. Really important from both a reproducibility point of view and an open science point of view, that we are saving all of our commands, our R code in a script, and that we're sharing those scripts. All right. Now, you don't have to be the world's best coder. All right. Shouldn't matter. Please just share your stuff, and you'll see that I am not the world's best programmer, and I'll make mistakes and things as we go along. All right. So let's create a new script and let's actually do something. Okay. So just so you know, everything that I'm going to create is going to get stored in this folder that we're looking at in the files pane down here. And then as we work, I'll introduce other aspects of the RStudio interface to us. So let's start. We're going to go to File, and we're going to go New File, and then RScript. Okay. Alternatively, you can just click this little icon that's underneath the file icon. You can click the little down arrow, and then you want to do an RScript, right? So let's click that. And at the moment, this is unsaved, all right? So let's save it, and we're going to give it a name. So save, and then this will bring up whatever save dialog you have on your computer. So I'm going to call this, well, yeah. Well, actually, let's do something more informative than that. Live coding script, and I'm going to give it this extension .r, uppercase R. That will associate it with RStudio, and if you were to double-click the file in Windows Explorer or something like that, then it would open up RStudio for you. So uppercase R. All right. So now that's ready to be saved, and that's good. We're ready to go. Now, it's also really useful for future you if you put some notes into your script to say what you did, what the script's for, and so on. And we do that using the comment or the hash character, the pound symbol. Okay, so this is my script for the live coding session. Apologies, I have a mechanical keyboard, so if it's annoying whilst I'm typing, I do apologize. This is essentially hidden from R. R won't try and run that code. Was to run that line by clicking here on run, for example, it won't do anything, right? Because there's no R code there. So anything after this little chevron, this little hashtag symbol, just means that it's essentially a comment. It's going to be ignored by R. So everything after it is going to be ignored on the line. All right. You can maybe put in your name if you want. Okay. Whatever you want in here. Some notes. Okay. Right, so hopefully you've had a chance to install some of those packages, though you'll probably have a lot of these available to you. We're going to just have a look first. We're going to do some data import, and I'm going to show you different ways of importing data from different kinds of files. Then I'm going to show some work doing some stratigraphic plotting, and we'll talk a little bit about ggplot and some newer packages, or a new package for doing stratigraphic plots within R. A really powerful one called tidypaleo. Then we'll do some multivariate data analysis. I'll show you vegan and some of the associated packages around vegan. And then something that I've been doing a lot of work on is using additive models or generalized additive models to model the palaeolimnological time series. And I will show some simple GAMs that come from a paper that I produced a few years ago. And we'll recreate some of the analyses from that paper. And I've chosen particular data sets that come with some of the packages, but also things that you can load in relatively easily, because if you're following along or if I'm doing them here, then they're going to not take too long. So there'll be occasions where I've made choices that are particular for this live coding that actually we would change. And I'll try and point those out when you're doing an actual analysis, because I want things to work fast here. We don't want to be twiddling our thumbs waiting for code to run. Okay, so let's start. It used to be that we would advise people never to have their data in Excel. But I think it's getting to the point now where that's unavoidable, and it might be useful if you do have your data stored in Excel to learn how to read it. And I think Excel is ubiquitous enough that it's okay now to do it. So what we're going to do is I've got some in this data folder here. I've got a copy of some data from Smallwater, which is a very simple sediment core record. Okay, actually, I'll open up the CSV because you'll be able to see what it looks like. So it's got information about the depth, and then some geochemical data, and then the lead-210 in third year up here. Okay. Now, I'm going to show you how to read in these kinds of data. What you shouldn't be doing is, when I clicked on here, you have this option to import the data set. Be careful with using these, because we want the code to read it in here. we don't want to have to remember which buttons we click in our studio. So viewing it is okay. Maybe helping with this thing to get it imported is fine, but always check what code it's used to import your data and put it in your script. So I'm going to show you how we're going to read these in now using code. So typically with R, there are some functions that come with the base R software, but you usually will add to it through packages that you load with the library command or function. Now, we've already asked you if you were following along to load some or to install them. You only have to install them once. You might have to update them, but you need to load a package every time you want to use it. So in your scripts, you should see things like this, like library calls. You shouldn't really see an install.packages command here, all right? Anyway, so in your script, library, we're going to load something. So actually, let's put a little comment, packages for data import. And we'll come back up here and add stuff as we go along. So the package that we're going to use is going to be called read_excel. And the reason we're going to use this is it works with something called the tidyverse, which if you're familiar a little bit with R, is a group of packages that all work the same way. And it has no dependencies. So you only need this package to be able to install or work from Excel files. Okay, so let's load in that data from small water. And we need to assign the output to an object. So I'm going to call that small water underscore Excel so that we know the difference. Then this here is the little assignment operator. It's the less than or greater than symbol followed by a minus. Okay, and I think, yeah. So on my computer, and I think on Windows, you can do Alt minus. Oh, if I'm on the right thing, but Alt minus. And I think on a Mac, if you do Command minus, I think it's the same. That will insert the assignment operator for you. Okay, and then the function we're going to use is called read_excel. So this is something that's provided by this read_excel package. Right? And for those of you who are not that familiar with them, there are actually two different kinds of Excel files. There's an older format, .xls, and there's a new format called .xlsx. And if you're not sure which, you use the read_excel function, and it will figure out which kind of file you have, right? Because some people can send you the file with just the .xls extension, and it may be the new version. Right? In here, we're going to give it the name of the file. So we can do it relative to our project root, okay? So we're in this IPA, pre-IAL-IPA folder, and we want to go into data. So we're going to type data, yeah, data, / always use the /, and then it was sw.xlsx. So that's referring to the data folder, and then this xlsx file here. And if we just do Control-Enter, we'll run these lines of code. So I'm going to put my cursor somewhere on this line, and I'm going to do Control-Enter. Okay, might be Command-Enter on the Mac. All right. If you're unsure, just click on a line, and then you can do Run here. And then you notice that the code has come over here into the console. Right? So it's now been run. That's why I'm saying we don't really want to be typing stuff in here except things that we want to lose. Everything we want to have going into R that we want to save should be over here. Okay, so if we run this, it'll take a second. Two things happened. Essentially, but there's a blank line in here. It actually did something, but we didn't get any warnings. But in the environment tab over here, it's showing us that now we've got a new data object, and it's in here, and it's telling us that there are 48 observations, there are 7 variables, and if you click this little triangle at the side of the object, then we get an overview of the variables that are in the data set. So here we've got depth. This is delta 13C of the organic matter in the sediment, total carbon, delta 15N, total N, the dry weight of the sample that was dry weight, and here we've got the lead-210 in 3rd year, okay, or the year of the sample. And if we don't want to rely on this, if we want to view the file, then we just, or what's been loaded in, then we just put the name in over here and we run. and just hit enter, and this is what we get. So this is a special kind of object called a data frame, slightly special version of a data frame. It only shows you the first 10 rows, but it tells you a bit more about what kinds of data we've got. These are all numeric, and it tells us that we've got some more data, right? This is just a modern data frame. And you could put that over here and do Control Enter, and it would go and get run here, okay? So that was reading in Excel files. There are things you can tell it what each of the columns are. And if you're not sure, and I can never remember this because I don't really use Excel very much, in here we can do, if we want to look at the help for a particular function, if we're not sure what arguments we need to do to tell it to do something, then we just put in a question mark and then the name of the function that we want help with. Notice that RStudio has already started to fill out the name for me, and it will complete. Right, so save yourself some typing by using the completion tools. Tab or Enter usually works. Okay, so let's have a look at this. This is the help system. It's not that user-friendly because it's designed to provide you as a simple overview of what's needed as a programmer to provide things to these files, right? It's not the best way to learn R by reading these things, okay? But we were using Read Excel. We get some information about what this function does, and this is the main bit here. It tells us what arguments we have available to us, okay? So maybe I want to specify the column type so that I want to make sure that R knows what I'm reading in, because maybe it's reading it in wrong, yeah? I want to go and look at what I have to provide here for call types. So underneath this usage, because there are several different functions documented here, come down to the arguments, find the argument that you want here, call types, and then let's look at what it says. So it's saying, you know, either include a null or one of these options. So skip, guess, logical, numeric, date, and so on. So you can tell R that we want to skip certain columns and so on. So how would you do that? Let's just copy this. And let's just put them in here. So let's do call types. Oops, sorry, not that. Equals. Equals. Let me just put my thing on. Okay. So we're going to do call types is going to be equal to. Let's skip. Let's guess the first one. Then let's do. There were 7 columns. So let's repeat. How many were there? Let me go back to my console. We'll skip the dry weight, okay? So I want to have a double or a numeric, yeah, numeric for 1, 2, 3, 4, the next 4 columns. So let's put numeric in here, rep 4. So that's just going to repeat numeric 4 times. So I don't have to keep typing it out, okay? Then I don't want to load in the dry weight. So let's skip that. Okay, and then let's put in another numeric at the end, okay? And then notice I'm starting to scroll off the screen. This is an indication that your line of code is now too long. So what I would suggest is you either hit enter and bring it down to this level, yeah? Or, let's just undo that, you could put the whole argument on a new line, right? Organize your code so it's easy to read. You'll thank yourself later when you have to come back and read this. And anybody you show your code to will thank you because it's nice and spaced out and easy to read. So now let's just run this code here. Anywhere on this little code block we can run, okay? To skip, so it guessed the first one for us if we weren't sure what it was. Those are our doubles, our numerics, and then skip the thing and then add in your, right? So we don't have to bring in all of the data if we don't want by specifying the column types. Okay. And there are other arguments in here, like you can skip certain rows and so on, okay? Always use the help to figure out how to use a function if it's new to you, all right? And then one other thing that we should just do, let's say you've got an Excel workbook with multiple sheets in, how do you list what sheets are in there? Well, we can use the Excel. Notice how it's already started to fill in for me. We want the Excel sheets. Let's hit enter. Okay, and then we give it our file name. So it was data sw.excel SX. Okay, if we run that line, so remember, Control or Command Enter. Okay, I get told, okay, I just got one sheet here that was this, and that's its name. Okay, and if you notice, if you just look down here, if you had a sheet, multiple sheets, how do you tell it which sheet to run? Well, that's via the sheet argument, probably. Let's go and have a look at that. Okay, so we just give it the name of the sheet to run, or an integer, which sheet is it? I would always recommend, it'll be in the order listed when it's shown here. I would always recommend that you do it by the name, not the number. Okay, so if I want to make sure which sheet we're going to load in, we're going to do sheet SW. Okay, and it loads in that one. Okay, so that's if you've got Excel data. Quite often you'll have data that's provided to you in a text file, and let's just put another comment in here. So reading from Excel. So often you'll have data, some data that will be provided as text files, like as comma separated or tab separated files. We need another, well, we could use base R to do that, but we could also use the readr package for that. Okay, so let's reading from plain text files. Right? And there are lots of options available. I'm just going to show you a really common one, which is to do this from CSV. So let's go back up here and let's add another package that we're going to use, the readr package. That's like the big brother of the read Excel package, but it's for text files. So let's load that. Okay, now let's come back down here. The reason I always put all my packages at the top is that as soon as I open my script, this is the packages, I can see what packages I need. And if I have them all listed at the top, I can make sure that they can all load. And if I don't have a package installed that I need, then I can quickly figure that out rather than having to figure out why I'm in my script. So put the packages that you want right at the top of your scripts. Okay, let's read from a text file. So the file we're going to look at is exactly the same kind of data again, but we're just going to look at it as from a CSV, just to see how that is done. All right, so I'm going to create a new object called CSV, because this is the, you don't have to call them this, it's just so I can differentiate between them. Okay, and I'm going to use the read underscore, and I want to read CSV2. If you're in a country where CSV files, you use the comma, like I am in Denmark, people use the comma as the decimal point, then if you've created your file on that computer, you might need to use read CSV2, right? So if it doesn't work with CSV, try CSV2. But that's just because we hear people use a comma for the decimal point instead, all right? So hit tab to complete that, so we get this. And let's go in, let's load our data, and it's sw.csv. Okay. And let's run that. It takes a little bit longer to read the data in because it has to parse it. The computer has to read what's going on. And notice this, we have slightly different behavior now. Reading in text, where you've asked the computer to infer what the text structure looks like, is always error prone. And so what it is being very verbose and telling you what it did. So it read 48 rows and 7 columns. Well, that's okay, that's good. That's kind of what we thought. We're in here. It's then telling you what it's read in. So it's read all 7 columns and it's read in as doubles. Okay, so numerics. And if you want, we notice we haven't specified any column types. So we could specify those now. And so we have a little bit of a shorthand to specify what kinds of column types we have. So it's using the same argument, col types again, but now, and I don't know why they haven't implemented this for read Excel, it would be useful if they did, but we can just go D, 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 D. So now we've got 7. It's 1, 2, 3, 4, 5, 6, 7. 7 doubles or numerics. Let's run that again. Okay. So now we don't get anything other than a couple of blank lines, which I think is a bit of a bug. I don't know why they keep putting them in. But no, why is it important? I mean, it read the file fine without this information. Why have I suggesting that you should use col types? Okay. Well, let's say the file on your disk changes. So I got sent this by a colleague that had put the data together for me. quite a few years ago. Maybe that data, there was something wrong with it, and they update the file, but they've changed the number of columns that are in the file, or put them in different orders, or they've just, something's happened and the data are no longer all numerics, right? By specifying exactly what kind of data I'm expecting, this will throw an error. So I think it's, is it C for character? Let's try that. Oh, well, I don't know why I didn't throw an error there. Maybe that's the wrong one. Let's try T. Okay, yeah. So T, it said we've got a problem. So instantly I get a warning message telling me we've got a problem with this file. So now I can go and give the name of that object that we read in. I can have a look at the problems. Okay. I don't know why I didn't read it in this. Oh, I know why it read it in this character. Anyway, here it was expecting a time and it read in some number, right? So it's telling me that we've got a bit of a problem here, right? So by telling it what the data types are, if there's ever any problem with the data, when you try and reread it in, you'll instantly get an indication that there's a problem, right? So be explicit, you'll thank yourself later. Okay, so let's read that back in. Right. Now, though most of you here are probably too old to remember Cornell condensed format files. Those of us who are of a certain age will have learned to hate these things passionately. But back in the day, our data were actually stored in very weird text formats, because when a lot of the software and the programs that we used to use before fancy interfaces like C2 and so on, they were actually generated using code that were on mainframes and big computers that had to be loaded in through punch cards and things. Space was a real problem then. Storing data in memory and loading it in was a particular concern in the 70s and 80s. And so, but these formats that are really old legacy formats still hang around. You'll still probably find data in these formats if you start collaborating with people more broadly, or a particular kind of program might need to use this format, right, to get it to work. Thankfully, that's changing a bit now. But in here, I've got two Cornell condensed files, and we're going to look at two different ways that we can load in these things. I'm just going to show you what these files look like. Okay, I'm just going to open this one. So let's open with a text editor. Okay. Okay. So hopefully you can see this, but this is the surface waters acidification project, main diatom data set. So this is the one where they've actually got lots of water chemistry associated with it. So it's got 138, and these are the diatom data in percentages. But there's this weird thing here which tells us how the data are. And then the data is stored with all the zeros dropped. So these are all the observations for sample 1. This is species 4, species 7, 8, and so on. And then this is the percentage of that species. So this is species 257, this is the percent. And then if you scroll down to the bottom of this file, all the way down here, let's go and grab this. Okay. At the bottom, we have all of the species listed. So you'd have to go through here and count 257 to find out which species it was. And then these are the samples. So the first sample, that was sample 1, that would be this Swedish site here. That for some reason, I think the Swedish sites all had numbers, okay, for the site code, and there was no name. So these are the kind of old formats that were, paleo data was universally, well, okay, within palaeolimnology, pretty much most of the data would be provided in this kind of format back in the day. All right. If you have these things hanging around, you probably want to read them in. And that's getting a little bit more and more difficult as the years go on. But there are some options in R. Okay, so the first option is just to use a simple, not that one, library, just to use a simple implementation that's in vegan. So vegan is the kind of R version of Kanoko for doing multivariate data analysis. But in here, we have a read.cep function to do this. So let's load vegan. These little red messages that it's saying here is just saying it's loading some support packages that vegan requires. So vegan requires permute for permutation tests, and lattice for some extra plotting utilities. All right. So let's go down, let's try and read. We'll read in both of these files, but I'll do them in different, with different functionalities. So let's reading Cornell condensed. Cornell condensed. Okay, so in vegan, the function that we want is called read.cep. Okay, let's assign this now. We're going to do this to swap 138. Let's call it 138. Okay? And remember, we just need to give it our file name again. So it's going to be data and then swap 138.cep. And this is going to take a few seconds to work. This is a pure R implementation, so it's pretty slow. So let's run this. And it will take a few seconds to load in. Maybe more than a few seconds. Okay, there we go. So here we have 138 observations, 276 taxa here. And this is a proper old-fashioned data frame. Type the name swap 138 in here, you get all of the data spat out into the screen, so don't do that. Using the head command, or actually, let's use the head command. So if we just want to show the first few rows, then we can do that. But remember to also limit this to the first few columns. Let's just show the first 6 species. Okay. If you're not familiar with subsetting, this is just a way to say, which rows do I want? Well, I don't need to put anything in here. I want to return everything. Here I'm saying, just give me the first 6 columns. And then head is just going to show me the first 6 rows of that subsetted data set. Okay. So here we go. These are our site labels, and R doesn't like row names that aren't that don't begin with a letter, so it's added X to each of them. But these are the diatom codes. These are the old diatom codes from the ECRC in UCL in London for the different things. So these AC, what's that? I can't remember anymore. This just shows, maybe it's acnanthes. Okay, just shows how out of date I am now. Okay, so that's that file loaded. You could see that it was pretty slow. I mean, this is a relatively big data set as far as paleo goes, but that was pretty slow. There's a much faster version in a newer package that Jari Oksanen has produced called SEPReader. And it's in a different package because it used to be in vegan, and then we moved it out because it was causing us problems. And it may actually get dropped off CRAN if we still have problems making the package available there. But if it does get removed from CRAN, it will be on GitHub. Okay, so it's called SEPReader. Let's just load that. Remember, if you've not got any of these packages, you'll have to install them. Okay, but we loaded it now. Let's go and load the swap 138 data again, and we'll see just how much faster SEPReader is for doing this. So let's stop typing. Let's go and copy and paste. Okay, so exactly the same command again. Okay, that finishes in seconds, and that's the difference between like R code and compile. This is, in this case, it's compiled Fortran, so it's really fast. Right. While we're here, let's load the environmental data. So let's put in a comment. So fast swap species data set. So this is the training set. And then let's load the environmental data. So swap environmental, it's like lake chemistry, lake water chemistry. Let's load that. And I'm going to copy this because we just need to change one of the things. And I think that's because some of these variables were log transformed. So they've already been processed for us. Okay, so let's run that. Oh no, let's not do it into swap 138. Let's put that into swap env. Okay, so now we've got the environmental data as well. Okay, and let's look at the swap env data to see what that is. Let's have a look. So head, remember, just shows us the first few lines. By default, it's going to show us 6. If I want to see the bottom of the file, then I can use the tail command. Okay, so those are the last few lakes. And if I want to do, say, 10 of them, then I think it's n equals 10. If and I'll get 10 rows instead of 6 or whatever the default is. Okay, so hopefully that gives you some idea about how to read data in. One of the things I'm not going to cover, partly because we don't really have the time here, is how we might pull data in from like online databases, things like Pangea, Neotoma, and so on. So just some adverts for them. There are packages for working with Pangea, working with Neotoma, and so on. There are packages that can automate you getting the data from those databases. So always check. There are some papers available as well, which kind of go through them. Lots of helpers available online for those things. But that's the one sort of thing I've kind of left off, right, is sort of accessing from databases. But hopefully the commands that I've shown you here kind of can get you started loading in data from a range of different formats that you're likely to encounter. All right. But just note that this is not all of it. All right. Okay. If there are any questions, I'll just hang on for a second and you can unmute yourselves and shout. Otherwise, we'll move on. Okay. Hearing none, I will move on. Right. Something a little bit more interesting. Let's. I'm going to have. This is going to be part 1, and I'll put part 1. Let's just put little breaks in here so that when I upload this to GitHub, you can sort of follow along. So that was part 1. Okay, and we're going to have part 2, stratigraphic plots. Okay. So I will say stratigraphic diagrams are not the easiest thing to make a good version of. There are things like C2 and Tilia that will help you create graphs, but you have to work at them. And also things like C2 and Tilia, you're clicking around in an interface with the mouse. Those are not reproducible things. So it might be worth using R to create stratigraphic diagrams, but just remember you're going to have to be using code to play with them. All right, but I think you will see that you can get some pretty good output from these things. Okay. Right, so we're going to start off. We're going to use a few packages now. We're going to use my analog package in a little while. We're going to use the dplyr package, and so dplyr is for data manipulation, and it should already be installed if you've installed the packages that I've suggested you install. And then we're going to use ggplot2 as our plotting environment, and you'll see why. We're going to use tidipaleo as well. I might as well put that up here as well. Library tidipaleo, spelled like the North Americans. So let's just load these packages, and for the most part we can ignore these things. So this is just analog being silly and telling you what version of analog it is there every time you load it, which is a bit of a pain. dplyr is just telling you it's masking some things. So it's just replaced these functions that are available in the base version of R. So just be careful if you want the base version of that flag, and so on. But just don't ignore these things in red that get shown up, but try to understand what they mean as you're working along. All right. Okay, what you want to be looking for are any error messages. These are not errors, these are just warnings. So the first thing we're going to do is I'm going to show you what analog can do, and this is going to create stratigraphic plots using the lattice package for plotting. So let's do analog and strati. It's not that, it's stratiplot. Okay. So we're going to load up a data set from the Abernethy forest. So this is the data set that comes from, I think it's from Hilary Burks, that was provided, and Rolf Matthews. Yeah, Hilary Burks, Rolf Matthews, that John Burks provided to me. So we're going to load Abernethy. So that's a data set that comes with analog. And so it's not one that we need to load in using the code that we've just done above. And I'm using this just because it's a nice, well-behaved data set for plotting with. All right. Okay, so want to do a couple of things. We want to get hold of the data. So if you look at Abernethy, there's a whole load of pollen data, and then we've got the depth and the age built in here. And typically you'll want to remove the depth and the age, or the things that are not associated with the species. You want to get rid of them, put them somewhere else, just to look at the species data, all right? So we're going to do that now. We're going to do a remove depth and age and store them. So we're going to create what this is like the metadata, let's say. Let's call it a metadata. It's not really metadata, but Abernethy. Okay, so we're going to take our Abernethy data set, and then we're going to use this thing called the pipe operator. And you'll see this within the within the tidyverse framework of packages. You'll see this used a lot, and I'm going to show you what it does in a second. Okay, so I'm going to take that Abernethy data and pipe it into a function. And that function is going to be as Tibble. So that's going to create one of these modern data frames. Now, what that is going to do is going to create some code that is essentially going to be the equivalent of this. So I'm over here now, Abernethy. So it takes the thing on the left-hand side and pipes it into the first argument of the thing on the right-hand side. So we can just chain all these things together is essentially the idea here, right? And so you'll see that used increasingly in code online. Right? And then what we want to do, because we want to just select certain columns, we want to get rid of depth and age, we need to select those ones to store them somewhere, okay? So in here, we want to give age and depth, okay? And then anywhere on these three lines, we can hit Control-Enter. Right. Let's just close that. Now we've got our new object, ABBA-META, and we've got our data. Let's have a look at what that is, ABBA-META. Okay, now it's one of these modern data frames that just only shows you the first 10 rows. We've got our age in, I think it might even be uncalibrated radiocarbon ages, and then some depth, all right? This data set was published in 1973, I think. Okay. Right, so we've got the metadata stored now. Now we can actually do some processing. When we're creating a stratigraphic diagram, you typically don't want to be showing all of the taxa, all right? And certainly within R here, where you're having to display them on screen, you aren't going to want to show the taxa. So how can we choose the most abundant taxa that we want to, you could choose whichever taxa you wanted to. We could just go ABBA subset, we could do whatever. And then I could put in here the species that I want. I could just list whichever species I want. So I don't know, maybe I want Betula. Oops, start typing over here, Betula. Betula. And maybe I want, for some reason, Ulmus, right? So you could list exactly which taxa you wanted, but often you don't want to choose just very specific taxa. You might want to choose taxa that have specific properties. For example, you might want to show only those taxa that reach a certain percentage abundance and which are present in more than just a few samples. So one way we can do that is to use a function from my analog package called choose_taxa. So we're going to create a new version of Abernethy now called Abernethy 2, which just contains the things that we want. So let's go to Abernethy, okay, use our pipe. We're going to select to get rid of now. We want to remove age, so minus age, and we want to remove depth, because I only want to be working with the age and depth variables. Right? Okay, so that's going to remove them. Now we're going to pipe that onto the output from here is going to get piped into the next function, which is this choose taxa that comes from analog. Okay, so I want to have the number of occurrences has to be 5 or more, and the maximum of, this is a bit counterintuitive, but I called it max abund. But basically, this is almost like it has to reach its maximum abundance, has to be at least this value. Yeah? So it has to be at least 10%, say. Okay. And then we've got rid of age and depth. We'd really like that age and depth information back. So let's bind that on. Let's stick on those columns for age and depth, and they come from ABBA meta. Okay. So we got rid of them up here. Now we're gonna, and then when we were doing our summarizing of the data, we got rid of them, but now we're going to stick them back on, right? Because yeah, this might start to drop some of these depths. So you don't want to be doing this on your age and depth columns. Okay, so let's run that. Okay, so now we can see this has retained 12 variables. So that suggests to us that there were 10 taxa. Okay, so let's have a look at that met those criteria. Let's have a look at ABINEFI2. Oh, and it's now become a tibble. Sorry, it's become an old data frame. So we want to create a tibble. Let's turn it back into a tibble, say. Okay, we rerun the whole thing. ABINEFI2. Okay, and what I was doing here, I was just to go back through my commands to rerun it without typing. Okay, so it's what it's saying. We've got Betula, Pinus, Sylvestris, so on. And then the things that it's not showing are Cyperaceae, Artemisia, and this Rumix acetosa type. And then our age and depth data that we put on at the end. Okay, so now we've got 10 species or 10 taxa that we want to plot, and we've got our time or depth variables to do something with. So let's create a stratigraphic plot now, and we'll do that using strati, if I can type, stratiplot. And we want to order them by the age variable, and so it takes a formula. So you want to order by age, and then I want to plot everything. So we use the dot, everything, but I don't want to plot the depth. So let's get rid of that, okay? Maybe you could have put depth over here, and then you don't want to plot by age, and so on, okay? And then we need to tell it what data to use. So our data set is coming from ABINEFI2, okay? And we can tell it what kind of plot we want. So let's just poly. Let's use polygons. Okay, so let's run that. So that creates this in a tasteful shade of blue. Okay. This kind of replicates the sort of thing that you might have got out of Tilia, except Tilia would have drawn this in black. Okay, or maybe in yellow and blue if you're that old like me. Okay, so that's a reasonable plot. It's not great, but it does the job. There are better things, but this is an option that is available in R, and it's something that I've written. Much better, though, I think, is to use the Tidy Paleo package these days. But you have to know a little bit about ggplot to work with that one. Right here, you have to know a little bit about lattice to work with this. Okay. Right, so let's have a look at the Tidy Paleo.
Sorry.
Yep.
I have a question.
Please go ahead.
You. About the plots, I am wondering if there is a way to create a synthetic plot with R, like a summary plot, as we can do in Tilia, because in R, I cannot find a way.
So can you just explain what that was? So what kind of plot?
The synthetic diagram, so that you put like, for example, 3 different types of vegetation that sum up to 100.
Okay, I see what you mean. Yeah, you might be able to do that in the Rioja package. So I think there's a way to do that, and that's a very good point. I will make a note of that, and I will add some notes to the GitHub repo. There might have been some teaching materials that Steve Juggins and I created, and I think Steve might have shown this. We ran before the IPA meeting in Glasgow in 2012 or something. And so I'll dig out that information and see if I can find or remember how to do that with Rioja.
Okay, that will be great. Thank you.
I'll have a look and see. And there may be an option in the Tidy Paleo package as well, but I'm not as familiar with that. But there might be an option.
I'm not familiar with that package. Can you please write it in the chat, and then I can.
Rioja or Tidy Paleo?
Ah, okay.
I'm going to do that now. I'm actually going to talk about tidy paleo now. Okay. Rioja is it's this Rioja, like that. That's the name.
Yes, Rioja. Yeah.
Rioja, that's Steve's package. Yeah, and which
Thank you.
also does stratigraphic plots. And I was showing you my thing, and I'm going to show you Dewey Dunningham's tidy paleo, but you can also do stratigraphic plots in Rioja, and Rioja is good for them as well. Okay, so other options. But I'll try and hunt that out for you, because I know the kind of figure that you're looking for. Yeah.
Thank you.
Oh, okay. Any other questions before we have a look at tidy paleo? No. Okay. Right. So I've loaded tidy paleo already. Yeah. Let's just double check that these are all loaded. Yeah, we did all of that. Okay. So this is the tidy paleo version. Okay. So tidy paleo uses ggplot. And I don't have the time here to explain ggplot in a lot of detail, but I'll point out some of the key features as we go along, okay? The first thing we're going to have to do is we're going to have to turn our data from this wide format, like we have it here, where there's a column per taxa. What we're going to have for ggplot, and if we're doing any kind of sort of statistical modeling where we want to model all of the different species, we're going to have to stack these columns one on top of the other. We need to take this wide format data and shrink it down into a long format data. And I'll show you what it looks like if you're not familiar with that. In the Excel world, this is called a pivot table. But we're going to create this long version. So I'm going to call it abalong for my data. And I'm going to show you the whole thing. So this is exactly how the sausage is made, using the original Abineffy data set, okay? And this just, I think, illustrates the utility of using this pipe operator to sort of step out the sequences of things that we want you to do. So we're going to do the select option again. And I mean, I can just come and copy some of this. So let's go and copy this bit and that bit. And let's copy that bit, actually. So I've just copied the code that I was using, but now we're going to, and to do this, actually, we need another package up here called tidyr, okay, tidyr. That contains this function, or a function, it contains several of them, but it contains pivot longer. We want to go from this wide format to the long one, so we're going to use pivot longer. The way pivot longer works is that we tell it which columns we want to pivot, or conversely, which columns we don't want to pivot. So I want to stack all of the species, but I want to have the age and the depth information repeated for each species that we stack, right? So I want to pivot the taxa columns. I don't want to pivot the age and depth. So it's easier here to tell it which ones we don't want to pivot. Okay, so we tell it through the calls argument. We use the exclamation point or the bang to say not these, and then we give age and depth as a vector like that. All right. We're going to create a new column, which is going to be called taxa, that's going to contain this information about what the species was. Right? So we want to call it, we want to tell it that we want a column called taxa. So we're going to do names to, these are the names of the data frame. Yeah. What variable are they going to be put into? So names to taxon. And then finally, we want what column are we going to create that's going to contain all these data points? So we do values to is going to equal, let's call it rel underscore abund. Oops. Let's put that on a new line. Okay. Abund. So that we're going to create a column now called relative abundance. All right. So let's run all of that. Let's see what it does. So most of this we've already done. Yeah. The last step here is what's creating this long format. So let's have a look at what that's done. Okay. So it's taken all of those Betular pine data and stacked them, right? This is the first sample from 5,500 years, radiocarbon years ago. This is the depth, and then these are all the taxa for that sample, okay? So we didn't pivot these two. They've not ended up in the taxon column. And then the data for that sample, so these values here, they've got put into here for this one, into relative abundance. And so it's got all of them now, are stacked one on top of the other, with age and depth repeated for each column of our original data frame. Right? So now we've got 480 rows, 490 rows, but only 4 columns. Now, this is the format that ggplot wants, because we want to create a separate panel for each taxa that we want to draw, right? And so this is just how we want it, how it's needed to be. Internally, Stratiplot is doing all of that for you here, right? So to get it in the right format for the lattice. With Tidy Paleo, it's much more flexible, but you have to create the structure that you want. Okay, so let's now take Avalon and let's pipe it into ggplot. So that's, you pass in the data. So this is the thing that's going to get passed to ggplot. Then we have to tell it which variables in our data set are going to get mapped to the X and Y, all right? So if we look at on here, we've got our X on this panel from the Stratiplot. We have the relative abundance is on the X-axis, and then on the Y-axis, we've got age here. So let's do that. Let's map age to the Y-axis and relabund to the X-axis. So X is going to be relabund. So that's the mapping there. And then what, comma, and then Y is going to be age. Okay? So we're specifically referencing the variables in this long data set. All right? And if we just do that, it's actually not going to do anything. It's just going to create this. All right? And it's not going to do anything because I need to put especially not if I need to do this. So to create a mapping, we have to wrap everything in this AES function for aesthetics. So the X aesthetic is the X-axis. The Y aesthetic is the Y-axis. And there are other aesthetics that we can, like color and things that we can map variables to. But even if I do this, it's not going to do anything, right? It's just going to create a thing that we could draw in, right? With ggplot, we add layers to the plot, right? That's what we do. And those layers are defined by geometries or geometric objects or geoms, okay? And the Tidy Paleo, it provides some geoms that are suitable for working with paleo data. So I'm going to first do another kind of one. Here we want column, these cols, so they're creating like bar plots in a sense, using segments, and I want them to be horizontal. Yeah, so that's what I want. And notice there are other ones here that are created, but I want these segments horizontally. Okay. And then I don't have to do anything. I do need to tell it, if you notice when it plotted this as you would on a graph, numbers increasing as you go up, but because this is an age variable, we want time to go the correct way on it from a stratigraphic diagram point of view. So we want the youngest, the smallest numbers at the top and the oldest numbers at the bottom, the biggest numbers. Let's start scale. So it's scaled, whoops, this is another layer. We're changing the scale on our plot using reverse. And then we want to create what we call a small multiple. So we're going to facet, we're going to create a panel for every taxa that we want to plot. So let's just go back here. Each of these is called a facet, or these are small multiples. You can think of these as an individual plot, and we've just got lots of them next to one another. So each one of these panels is a small plot, and we stick them together. So in the wider data visualization world, we call that a small multiple. Okay, so there's a special thing for doing facet. And because this refers to species information, we want to use the facet abundance, and we want the horizontal version. Okay, so facet abundance H. And then we need to tell it the variables that we want to put on. So I want to map by taxon. So it's going to create a panel for every species. And we do that using the vars function. All right, so like this. Okay. So notice we're building up the layers. The only thing to mention is that in ggplot, that's a bit of an older package now compared to this pipe paradigm. and it uses the plus instead. And you're not taking this and adding it to that and adding it to that. What you're doing is you're creating an object and just adding layers and layers and layers to the plot as we go along that modify things. So for example, if we just run this one here, just run that. Oh, sorry, I need to do all of it. Let's run all of just that bit. Then all of the data gets put onto the one panel, all right? Notice the axis is wrong. If we add on the next layer, that sorts out the scale for us. And then if we run all of it, now we get our small multiples, and this takes a little bit longer, but this is now our small multiple plot. And this is better than the Strataplot one, I think, partly because you've got the nice grid behind. I think it handles these things better, the scales, and does a better job of positioning the little labels in here. And TidyPaleo can do a lot more than this, all right? I really recommend you look at the webpage for TidyPaleo, which has lots of support for creating different kinds of plots. But I'm going to show you one more kind where we're just going to recreate the classic sort of Tilia polygon style. Okay, and I'm going to copy this so I don't have to type it all out again. And we're going to change one thing. So we can come in here and we're going to not use the little columns or bar plots as it would use. We're going to use the area. So we want a geom area, but we want the area to go horizontally again, right? So we use the, okay. And while I'm here, I will note that those of you who like to use exaggerations, like to show where you've got really low abundances, to sort of zoom in a bit and draw something that's maybe ×5 or whatever, then there are these exaggerate versions here as well for that if you want them. Okay, so I'm going to use area H. Let's run that. Takes a little bit. This is just because of the graphics tool that it's using underneath the grid. It's a little bit slow. Okay, but here we go. This is the kind of classic sort of Tilia kind of plot that you get, except with a slightly modern twist. All right. So lots of functionality is available, but you do have to do a bit of work to get your data in the right formats, to manipulate the data in a certain way to get it ready for plotting. Okay, and lots of things. One thing I will say is you want to export these things, you can just save them here. Okay, but a better way of doing this is for things like ggplot, particularly, and I'm going to focus very much on ggplot here. Let's save the output. Let's just call it plot1. Okay. So notice now I've done that. It hasn't displayed anything. If I want to get it to display, I have to type the name and hit enter. Now it will redisplay. But now I can save that to disk. So I can go gg save. I can give it my file name. So let's call it Abernethy. Let's call it stratplot. And I'm going to create a PNG. You could create a PDF by putting PDF here. Okay. And then I'm going to tell it what I want plot1. Okay, let's run that. So it's told us what size. You can use the height and width if you want to tell it to do it as a bigger file. Let's go and have a look at what it's done. In files, in here, and we've got this Abernethy stratplot.png. So that's a ping. You could have a PDF, SVG, whatever you want. Can be out here. PostScript, like EPS files, the journals, or PDF is probably what you want. PNGs if you're doing it for the web. Okay, we've got about half an hour left, and I already see I'm running over time a bit. So any questions before we move on? Hearing none. Okay, so now I'm going to do, oh, yeah, go ahead.
I have a question. Is it possible to add have the both axis, age, and depth at the same time?
Is it possible to add multiple axes? You should be able to. So there is a way to add secondary axes. I'm pretty sure TidyPaleo has that. There is a way to do it. I think you can also do it in Ryoka and Stratiplot as well. So you can do it. I'm just not 100% sure how it's done now. But there is a way to add like a scale. So on this plot, it would have, I think the axis would get, the secondary axis would get put over here, and it would have depth on. Okay, but I'm not 100% sure exactly how to do that. I will find out after we finish, and I will let you know how to do it. I'll add to the script how to do that. So go back to GitHub later, and if I can't work it out, I'll leave a note to say I couldn't work it out and there wasn't a way of doing it, but I'm pretty sure there is. Okay.
Perfect, many thanks.
Okay, so part 3 is going to be a whistle-stop tour of some multivariate analysis in vegan. All right. So let's load vegan. Okay, and we've already got it loaded, but that's good. Okay. There are a couple of things I'm going to do. I'm going to show you how to do a little bit of ordination. Now, I would teach multivariate statistics. I mean, on the London course that we used to have in UCL that John Burks and I taught, we did ordination in 2 or 3 days. I'm teaching a course on this in September in Aarhus, or probably in where I actually work, the University of Aarhus anyway. And we're going to do 5 days of this. So clearly we've got about 15 minutes. I'm not going to be spending too much time on this, but a big package, it's a big topic, but I'm going to show you some of the things that we can do to look at paleo data, to summarize it and display it. Okay, but I'm only scratching the surface here. So we're going to do, first off, we're going to do a PCA of the SWAP lake water data. Okay. Now, vegan doesn't have a function for doing PCA that's separate from the other functions or for doing correspondence analysis. It just uses RDA and CCA, and but if you don't give it any predictor variables or any constraints, then you get PCA or CA, right? And we'll see that now. So let's have a look at SWAP. We're going to call this PC for principal components. We're going to do RDA. And the way this works then, we just give it the environmental data that we already created in the previous section. And then because these data are all these variables are all measured in different units, then it's probably better to scale them, i.e. standardize them, so they all have the same mean and the same variance, so that they're measured in big units don't dominate the ordination. Because pH is measured in small numbers, whereas some of the other things can be measured in big numbers, like conductivity and things. And then conductivity would dominate. So we're going to standardize these here by saying scale equals true. So this has done a principal components, even though we did an RDA analysis. We used the RDA function. Okay. So if we just type the name of the object that we've fitted, we get a little bit of information. So this is the R code that was used to generate it. Inertia here is like variance, but actually it's correlation here. So how much of the total correlation in the data set between all the variables is there? And by convention, there are 10 of them. We've got 10 there are 10 axes because there are 10, I think 10 environmental variables. So we can decompose this data set into 10 principal components. And so there are 10 bits of correlation or 10 bits of variance. That's just the convention. Right? Over half of that is shown on the first axis. So these eigenvalues tell us how much of these numbers are explained by each axis. So just having one variable can explain about 56% of the variation in the chemistry data. Right? So how do I find that out? Well, I mean, I know that from the eigenvalues, but we could also look at that by doing this thing. Using the eigenvals function from vegan, and if we pass it the PC, then we run this. Okay, it gives us, repeats the eigenvalues, but now it says what is the proportion explained. So that's proportion out of 1, so 56%, another 21% on the next axis. Okay, so that we have, for example, we can explain 3/4 of the data by just having 2 axes, the relationships. All right. A way to visualize that is through a scree plot. Okay, and there's a scree plot function. Okay, So we get a little plot like this. The length of the bar is related to the eigenvalue. It is the eigenvalue. And what we're looking for here is where the slope starts to change shape. And so this suggests that maybe 2 or maybe 3 axes are worth using. And we can add on something called the broken stick, which is just like what would you expect? How much variation would you expect if there was no structure in these data? So we add on broken stick. So this suggests here that 2 is okay. We don't really need that third axis, right? And even the second axis is borderline, but we'll keep it to get a nice ordination diagram. Okay, let's plot it. So we're going to use the plot function. We're going to plot the swap PCA, and I'm going to show, we're going to display so in vegan, the samples, we call them the site scores. We want to display sites, and the variables we call the species scores. And this is just the convention that comes from Kanoko. Makes no sense. Species, when we're talking about environmental water chemistry, yeah, but that's just what we call them, right? It's the variables, right? So we're going to show 2 bits of information on the plot, okay? And when we do that, this is the kind of thing we get. And I don't have time now to go into a lot of detail about how you could make these nicer, but it's automatically showing these as you would expect an arrow in here. So these little plus symbols are the variables, the species, and the circles are the environment, the samples, the different lakes. Okay? We can get a slightly more traditional plot using the biplot command, or biplot function. And I'm going to tell it that I want to use text, or T, for the species. Okay? And I think these things are actually back to front, but we're going to use black and red as the colors, just to make nice red. Ooh, not read, red. Okay, let's run that line. Okay, and let's zoom in that so we can see. Okay, so now what we've got, these are all of our lakes arranged, and they've been ordinated in this way. So we can see that, you know, there's a sort of ionic strength gradient here. This is higher conductivity, more ionic strength waters, low conductivity sites over here. And then so that's the main gradient here. Things like calcium and so on is along this first gradient. The second axis here is the pH aluminium kind of gradient. All right, so there's sites varying in this direction are going to vary more in terms of their acidity. And so these are the very acid sites are up here, the more alkaline sites are here, and so on. Okay. And the angles between the arrows tell you how correlated they are. And so because there's like a large angle between aluminium and pH, that indicates that they're negatively correlated with one another. As the pH goes down, aluminium increases and so on. Whereas a suite of these ions over here, they all point in the same way because they all tend to, if you've got high magnesium, you probably have high chloride, high potassium, and so on. Right? Okay. Right, so that was doing a principal components analysis. Let's have a look now at doing a correspondence analysis of the diatom data. So correspondence analysis. With any constraints, then we get correspondence analysis. And correspondence analysis is suitable for species information where we expect the species to respond unimodally to the environmental data. All right? And essentially, this is going to show you something that's related to the relative or the composition of the species rather than the magnitudes of the environmental data or the correlations. So let's run that. We don't need to give it any extra arguments. There's an internal standardization in this, this thing here. It's all about relative contributions. So we don't need to scale anything. Swap, let's have a look at it now. So we get something very similar. Now inertia is in terms of chi-squares, so how much of the chi-square distances between observations are explained by the different axes. We now have 137 axes because there are 138, that's the minimum, so 138 sites. So we lose one here. We can, we have whichever is the smaller of the number of sites and the number of species, -1, okay? Because everything's centered. And you can see that there's a bit more structure in here. These numbers do not decline as quickly as they did in the PCA. So there's a little bit less structure. There was 2 main gradients in the environmental data, less structure in this particular correspondence analysis data set. Let's just go and plot this now to have a look at it. Okay, and if we look at this, we can already see that this is actually not doing a very good job. It's well, it is doing a good job. It's just identifying a couple of sites that are very different from the rest of the data. And this is one of the features of correspondence analysis, is it can get upset by site species combinations that are odd, the outliers, right? So an alternative way of looking at species data, in a way that I think actually works better for the kinds of paleoecological data where we got taxa like diatoms and things, is to standardize the data and then use RDA, like a principal components analysis. And we'll do that now. So I'm going to use what's called a Hellinger transformation, but that's essentially just square root transforming the percentages. And essentially that's all it's doing, okay? A little bit more to it than that, but that's, you can look at the help. So we're going to convert our data, we're going to Hellinger transform it, and we're going to do decostand. That's a function in vegan that will do these standardizations. So we want to pass it in swap 138, and I want to tell it that my method equals Hellinger. So now that's standardized, it's applied this special kind of transformation to the data. Now it's suitable for use with principal components analysis, right? Normally, you wouldn't use principal components analysis for species data. So now we can do swap hel PC for principal components. I can do my RDA on swap 138 underscore hel. There we go. And we don't need to standardize the columns really anymore. Yeah, we don't need scale equals true here. Let's run that. And let's have a look at the underlying structure. Okay. So now there's a little bit more here. This is first axis explains 10%, then 5%, then it trails off. Okay. So let's do our scree plot. Let's go and copy this. Let's go and have a look at that. See how many axes we should be saving. Okay. And this suggests, okay, that there's still a lot of more structure in the data, i.e. there's more information, there's higher dimensions in here than just the first 2. So we might want to go and look at multiple dimensions to actually understand all of the variation in this data set. But we can just focus on the first 2 because they explain the largest proportion of the variance. Okay. And as before, we can do plot, and we can plot the swap CA, what do we call it? Hel PC. So we can plot it and have a look at it, or we can do the biplot. Now I will say, creating nice plots in of these biplots is not the easiest thing to do, but there are some tools in vegan that will help you do that, and that's something we can't really go into today. Okay, but we could add text on here and so on for the different species, but it would get very messy. All right, so I'm going to leave that for now, but you can use the same code that we did for the original principal components up here using this. Okay, so let's now have a look at constrained ordination. So we've looked, let's assume we've done a bit more work. We're looking at we've looked at the variation within our data set, but now let's say, okay, how much of the variation in the diatom data can we explain with with the lake water chemistry data? So that requires what's known as a constrained ordination, where we have one matrix of predictor variables and we explain variation in our response matrix. I'm going to use the Hellinger transformed diatom data, and I'm going to use the swap water chemistry data as my constraints or predictor variables.
Sorry, Gavin, there's some 2 questions in the chat.
Okay.
There are 2 questions on the chat. So one by Joanna.
Yep.
Asking whether there are any good intro resources for doing this sort of analysis with paleo data that you would recommend.
Off the top of my head, not for paleo data. If you don't mind making the conversion to ecology, then there's numerical ecology in R, I think it's called, by Daniel Bocard and Pierre Legendre, which has a lot of stuff on vegan. There's stuff on my blog as well, and I'll put the link to that up. Then I see the other question here.
So the second question is, do we have to interpret the information lost by the components not considered? Is it useful to plot PC1 versus PC3, for example?
It is if there was structure in it. So I don't know, for this diatom data, then it's definitely worth plotting some of the other things. And the way you would do that is to use choices equals, and let's say we want to plot 1 against 3, axis 1 against axis 3. So if we run that, okay, no, that's fine. Just ignore the warning message. It's just that some of the species have got really no variance on this first axis. That's why they're getting the warning message. Don't worry about that. Okay, so now it's changed. If I wanted to plot 2 against 3, then I can do like this. Okay, and now some of these angles are getting set to be essentially 0. So that's why it's doing this. The errors, the warning messages, but it's fine. Don't worry about them. Okay. So yeah, you can plot. If there is more structure than just the first 2 dimensions, then yes, you should go and look at those extra dimensions.
Okay, and there's another question by Ricardo, who wants to know, why did you use RDA though instead of PCA, since you keep referring to RDA as PCA? And yeah.
Okay, sorry. That basically redundancy analysis is the constrained form of PCA, but if you don't give it any constraints, if you just give it the species data or the environmental data, then it is going to do principal components. Yeah, so it's done a principal components analysis. It's just that we use the RDA function because internally the code is just an extra line of code to do RDA once we've done the principal components. It works the other way around, but we just, rather than have multiple functions to maintain, Yari decided to have RDA that does the linear methods, which includes principal components, and then CCA is going to do the unimodal one, CA and CCA together. You'll see now that this is actually going to be an RDA where we're going to do our diatom data, so the Hellinger transform data. Okay, and now we're going to model it against all of the lake water environmental data. Okay, so this now has constraints. Yeah, we're putting a formula and we're saying use everything in the swap end. Okay, right? Yeah, that's what I want to do. Okay, so now notice the difference here. I'm giving it a response matrix and I'm giving it a set of environmental data. So I'm now going to look at the patterns that in the diatom data that I can explain with my explanatory variables, and that is RDA, right? Okay, but if I leave off all of this stuff and I just give it the species data, then I get principal components. Okay. What have I done now? Oh, probably because, oh, sorry, yeah, because it's swap 138. Hell, there we go. Okay, there we go. So I actually give it the species data, okay? And then this dot just means use all the environmental variables in our data set. Okay, so let's have a look now at what that's done. Okay. So now we get a little bit more. So this is actually the model that was fitted. So it includes all these environmental variables. Okay, this is the total inertia. So that's the, if you think of it as that's the total amount of variation in this particular data set. And we explain that much out of it. So our 10 environmental variables can explain almost 20 units worth of, 0.2 units worth of inertia. That works out to be about 30% of the variation in the diatom data can be explained using these environmental variables. Okay. And then it says that there is the rest of it is unconstrained here. Yeah, the 69% is unconstrained. That's structure that's left over. Right? And you'll notice that these are the RDA axes. So these are the ones that are related to the water chemistry. And these are principal components, and it's only showing 8 of them, the first 8. These are the unconstrained. You can think of these as being like the structure in the residuals from this regression model. And notice this here, this number is as large, slightly larger than the second axis. So there is structure left over in the residuals that we're not able to model here, given this suite of water chemistry variables, all right? But we explain, 0.9? So we explain about 15% of the variation in that thing. Okay? And we can have a look at that by looking at the eigenvalues that I showed you earlier for this one here. For example, we can use this. It's not that anymore, it's swap RDA. And we'll do model equals constrain. Is that right? Yeah. So we can explain about 49% of the variation that we can explain is here, and on that first axis, so 49% of 30% is that 15, right? Okay, now, are those relationships statistically significant? So there are a few things that we can do here. Oops, didn't want to do that. We have to do a permutation test, so let's tell it how many permutations we want. So this is using the permutation, the permute package to tell it. You don't have to do it this way, but it's just a nice way of pointing this out, because for more complicated analyses, you might have to constrain the permutations. And you do that using the how function in permute. Right? And I'm only going to do 199 permutations here. You want to do a lot more, but some of these things get a bit slow trying to do some of the next steps. So we use the ANOVA function, and it makes no sense. We're not doing an analysis of variance, but ANOVA is the way you compare models in the regression framework. So we use the ANOVA function, but I believe me, there's no analysis of variance here. We pass that object we just created to permutations, and then we want to do bi-axis. Oops. Oh, no, actually, we don't want to do that yet. Let's just do it. Let's just look at the overall significance of our model. Okay. Now that's really quick because I only did a few permutations, but that's our p-value. Right? So it looks as though there is some effect of these water chemistry variables on our diatoms. Let's have a look and see how many axes maybe we want to interpret. So we can do bi equals axis. Okay. This will take a little bit longer. What this is doing is it's looking at the first axis and saying, okay, how much variance is explained by the first axis, and testing that. And then it removes the variation that's explained by that first axis, and it tests the second axis. And then it keeps doing that. So it removes the first and the second axes, and then it looks at what it can do on the next axis, and so on. Okay. This is going slow today. It'll take a minute. Come on, you were working faster earlier. There we go. Okay, so this tells us that maybe down to axis 4, yeah, is statistically significant, is showing an interesting amount, but really most of the variation is being shown on the first 2 axes, right? And then if we wanted to know which variables seem to have the largest effect, then we can do what's known by margin. And this is going to repeat it, but it's going to, let's say, here we've got a model with all these things in. Oh, it's done it now. Okay, that's quicker. So for the pH, what it does is it has a model with everything but pH in. So it has all the other variables in. And then it says, if I add pH to it, how much extra variation do I explain when I add pH? So that's how much variation can be explained uniquely by pH. This is the unique variation that can be explained by TOC, and so on. Okay? So we can see most of these seem to be significant. Calcium and magnesium aren't. And that's likely because the variance inflation factors. So there's a lot of these variables are very correlated with one another. So you see things like conductivity, calcium, magnesium have high variance inflation factors. This indicates that calcium, well, if you know the conductivity, you pretty much know the calcium and the magnesium, for example. Right? So we don't need all of them in the model, and in fact, they're redundant. Yeah? So once conductivity is in the model, calcium adds nothing, magnesium adds nothing. That's what we've learned here. Right? So you could use this to maybe prune the model out, drop calcium, magnesium, and so on. Right? So in the interest of time, I had one more thing I was going to show, but it's a little bit more involved. I'm just going to show you a little bit of it. I'm not going to go through it in detail. I'm going to show you how to create what we call a time track. Okay, and I won't type all of this out. I will explain it as we go. Okay, and I'm just going to use some data. So there's similar data. It's the swap data set and then a sediment core from the Round Loch of Glen Head. And I'm doing this because I know that they've got the same species in common, and I haven't got time to figure that bit out right now. Okay, i.e. the diatoms are harmonized between these two data sets. This is essentially the same as the swap diatom data, but this is now a sediment core that Viv Jones from UCL worked on. Okay. Right, so we're going to use the time track function, and what we're going to try and do is we've got an ordination using the swap data, and then I want to then passively place the core data into that training set. Right? So I'm going to transform the data using the Hellinger transformation again, and I'm going to use RDA because this seems to work best. So let's do that. Underlying all of this, it's using an ordination from Vegan to do it. So this stuff should look very familiar to us. And now if we plot it, oops, there we go, let's plot it. This is what we get. So now the core samples, it's showing you where the sediment core projects in time. And there are ways to label these and so on, so you can know which is the most recent samples. Hint, I think it's over here, and so on. But there are ways to visualize where the sediment core samples project onto this ordination. This was an RDA, it was unconstrained. If we wanted to do something that's similar to a transfer function, but without actually doing the crazy thing of fitting the transfer function, we could look and see how these things, how does pH vary, and how well do these track the changes in pH? So let's do that now. So I'm going to skip that bit. Here's how we look at pH. So we're going to load the pH data from analog. And now we give it our diatom data, we give it our sediment core, but now we have to tell it the environmental data. And so I'm creating a data frame with just this one variable pH that contains the pH information. And now this is the formula that you would pass to CCA or to RDA. Right? So I just want to have now an ordination that's constrained just by pH, say. Right? Let's run all of that and look at the output. Okay. And because I didn't do any fancy coloring, this is now what happens. This is the ordination. So this first axis is constrained to be the pH axis. So any movement in this direction is going to show that increasing in acidity. Right? So this is just one way, and we could have done it for the whole swap environmental data set to see where, is it always following acidity, or is it maybe following the conductivity or the organic carbon axis? Okay, but this is one way to, without doing the transfer function, to actually visualize how your sediment core data is changing relative to this modern training set that we have as the background. And all we're doing is essentially we're projecting or placing the core data into the training set that we have available. There's no transfer function involved in here, right? So it's actually more robust than a transfer function, I think. But yeah, okay, right. A couple more minutes to go. I'm going to do the GANs. So this is part 4, and we're going to just spend a couple of minutes fitting a simple GAN. Okay, so I'm going to load some packages. And again, I'm not going to type these because my fingers are getting tired now. We're just going to load some packages. Gratia is a package that I've written for working with GANs, and MGCV is the package that we're going to use to actually do the fitting of the GAN. Right? Now, a GAN involves smooth functions of time, and rather than linear things, it's going to be a smooth, so it's going to be a wiggly function. We're going to load these data from the internet, so we'll grab that. And then we need a label for our plots. So I'm going to also put that in here. Okay. And I haven't got time to explain what that is. But it's just going to give us a nice plot for isotopes. Okay. So let's load the data. Okay. So we're loading the data from the internet, and now we're going to this. So this is just the small water data that we were looking at earlier as well. Okay, so let's do fit a GAM to these data. So if you've ever fitted a linear model, this should look pretty familiar. You give it your function. Here is our response. This is the different bit now. Rather than fitting a straight line, a linear effective time or year, I want to have a smooth function of year, right? And I could create a plot. Sorry, this would make it easier to understand why we might want to do this. So I'm going to create a plot of the small water data using ggplot. So I'll give it my data, map the year or the time variable to the x-axis, map the delta 15n to the y-axis, and then visualize it. Okay, so let's do that. Okay. So this is time going in this way, right? So I want to know what the trend is. Well, it didn't do very much for the first 100 years. Then we see a big change, and then it's done maybe some wiggling around at the most recent sediment samples. Okay, if you were to put a straight line through here, you'd miss most of the data, right? So a straight line is not the right trend. So if I want to summarize how the delta 15n is changing, I want something that's kind of going to go through the middle of the data points over time, right? That's what the GAM does. Okay? And we represent that rather than just putting year in the formula, we represent it as a smooth function. And here I'm going to use 15 basis functions. So it's going to have a wiggliness of 15, say. So let's run that. And let's visualize that using the Gradia package. So that's SW1. So this is our estimated smooth. Okay. So it's done a pretty good job of picking up those sorts of features. Okay. But it just seems to suggest that whilst there was this rapid change in delta 15n, the change at the most recent period in the sediment record is actually a bit more muted. Okay. Now, because these data are ordered in time, and this is the last thing I'm going to do, you can read more about it in my paper from 2018 if you want to know more about GAMs. Because these data are ordered in time, we should tell the model that before we do our fitting. These confidence intervals or credible intervals are actually too narrow because these data are autocorrelated. So let's correct that now with a different model that accounts for that. Okay, and it's the same model, but now we're going to use a slightly different function. We're going to use this mixed model function because that allows us to include these correlation functions. And because my data points are spaced irregularly, like most paleo data, spaced irregularly in time, we have to use this continuous time thing. And the data are ordered by year. The rest of it looks exactly the same. So let's fit that, okay? And let's plot it. And for various reasons, we have to plot the GAM object, yeah? Okay, so this is very similar, except now our interval here is a bit wider. It's reflecting the fact that we're not as certain as we were about where that trend goes. Okay, and I could add on the residuals here to show that this does a good fit. So residuals equals true. Okay, yeah, we can explain most of the variations. A little bit of variation in the top of the call that we don't do a good job of modeling. Okay. Why are GAMs useful? Well, GAMs are useful because most data in paleo is not going to increase simply as a linear function. Yeah, we often have these non-linear patterns of change over time, and GAMs are a really good way of summarizing that kind of data. Okay, I will stop there. I'll stop sharing. If anyone has any questions, I can answer them. Thank you very much for your attention.
Okay, thank you, Gavin, for that. We have two questions that are pending. So one is, does removing the redundant data improve your models?
Makes them more parsimonious. You don't have to remove them, but it makes them a little bit what we call more parsimonious if I was going to use it to do any kind of prediction or things like that. Also, in the context of that, like removing, say, the magnesium and calcium and things from that model where they had high variance inflation factors, it can make the regression coefficients be better estimated, i.e. they're less unstable, I guess is the terminology we use. And it's like in any like in a linear regression where you've got multicollinearity, that can cause problems. It can inflate the regression coefficients. It can have the same effect in an ordination. And so you would actually want to maybe get rid of things that are not, that you're not interested in. Like I don't need to have magnesium and potassium and whatever in my model if I've got conductivity. You can maybe leave those ones out, right? So they weren't adding anything. Whereas pH had a variance inflation factor of about 10, which is quite high, but I want pH in my model because I'm interested in how the diatoms responded to the acidity. So I would keep that, get rid of something like magnesium and calcium, and then maybe my variance inflation factor will go down for pH because calcium and pH will be related to some extent. Okay.
Okay. And lastly, from Ramina, how is the red curve calculated? I think this is from the scree plot. That allows us to know how many components we should consider. Does it depend on the number of variables, and is it helpful to detect if any variable is not relevant in the analysis and eliminate it?
Yeah, okay. So that's referring to these broken stick things. Let's just scroll back up and let's show one of them. Where was it? Yeah, here, let's show this. Okay. So essentially, if you think about, it's called a broken stick for a reason, right? Imagine a stick. Imagine you take like a ruler, like something like this, right? Oh, yeah, I'm not sharing my screen. Anyway, give me 1 second and I'll share that so you can see it, because that would be helpful, wouldn't it? We've been on Zoom for 2 years or more, and we can still make mistakes like that. Okay, right. So imagine we have a ruler or a thing like this that's like 1 meter long or something, and that represents the total variation in my data set. Now this is not a good one because this is metal, but if my stick was made out of wood and I just broke it randomly into pieces, and then I put the pieces in order from the biggest to the smallest, then this is on average, if you were to do that essentially lots and lots of times, from that length of wood, what is the length of the longest piece? And then the next longest piece. Well, it works out, you can do the math, it works out that on average, the longest piece will be this. And then the next longest piece will be of this length, right? So if my thing is 1 meter long, say, then this is the length of the first chunk. Now that's breaking it up at random. If our axis explains more variation than random, then it will be a longer piece of stick. Yeah, because if you think about what ordination is doing, it's taking our data and breaking it up into lots of little chunks. We've got the chunk associated with the first principal component, the chunk associated with the second principal component, and so on. So we've done the same thing as like breaking our stick. All right. This one clearly explains more variation than the first axis, than we would expect under the null model if there was no structure, and so on. The second axis does too. Okay, and this one is telling us really that there are maybe 9 or 8 or 9 axes that we might want to interpret. But that's probably overkill here, and that's because really we're looking at the relative abundance, and the transformation has kind of helped constrain some of these patterns. So another way to do it, again, look at the rate, the change in the slope. A really steep slope here, then it starts to shallow off. So that indicates perhaps the first 2 axes, okay? But how it's done is just by randomly breaking up the stick into random pieces, and there's a bit of math that tells you what the expected values would be, okay? It doesn't help you determine which components, like which variables you want to have in there. Remember, this has just been done on all of the species data. There were no variables in here, all right? There were no like lake water chemistry in here. So it doesn't help to determine that. What it really just helps to determine is maybe how much structure you have in your data set when you want to visualize it with the ordination diagrams.
Okay. Okay. Thank you, Gavin. Thank you, everybody. I know we've gone over by like 8 minutes, but that's not too bad. It was a very technical presentation, and I hope you've been able to follow. I think the link for the GitHub was already shared, and it will be shared again after this session. And I think we need to give Gavin our virtual claps for an awesome job done. If you need to reach out to him, I think his email is in the program, so you can just look at the program and his university email is there, and probably you can reach out to him and look at that data set. So thank you very much. Everybody who's been here, all our coordinators, thank you, Fernanda, for putting all this together and bringing this awesome panelists to us and sharing their knowledge with us. And Day Z is finished. We have now officially launched the PRE-IALIPA workshop, and we're looking forward to more interesting discussions. So I will hand over to Fernanda in case there's any